I guess we couldn't predict this error before, so anyway, thanks everyone. So that was actually a fantastic introduction by Chris. He covered many aspects in very good detail, so I can dive right into cross-validation. So, all right, there are 3 goals for today at the end of this talk. One is to learn what is cross-validation and why we need it, how to perform it, and what are the effects of making choices for a particular cross-validation scheme. And is there a bias that we will introduce in our predictions when we actually make a choice? Just 3 goals. So in order to understand what is cross-validation and why we need it, we need to understand what is generalizability. So Chris touched upon it quickly in terms of accuracy and regression error. So the problem stems from the fact that we have a the data we have available to us is small, which is usually called the sample. And what we would like to do, let's say this data is coming from a particular area, just to give you a real world example. We learn from this data, train our machine, and what we would like to predict is, what we would like to estimate is the accuracy on the unseen data. So you only start with what we have, and ideally what we would like to estimate is the performance of the machine or classifier on the data it hasn't seen before. That's the key challenge for machine learning. It is usually called out of sample predictions, like Chris mentioned. And we do this to make sure that our machine is not overfitting to the available data, and it's actually trying to learn the generic patterns that is in the data. So cross-validation is a technique that helps quantify the generalizability. So it's simply, let's say this is our available data. We keep some data, let's say from California, held out, learn from the other data, and try to make predictions on the held out test set. And we repeat it with the other sets of data, and hopefully with this process we can estimate its generalizability on the entire data. That's the predominant goal of cross-validation. So why do we have to do this? The main reason to cross-validate is because we know that the bigger training set actually leads to better learning. The more data we have, the more opportunities and the ability for the training classifier to learn. That leads to better predictions. We also know that we need a bigger test set to actually test its performance. If you were to give it easy examples or hard examples, we are not actually accurately testing it. We need to expose the classifier to full variability in the data so we can actually better test it. But key challenge is that they must be independent, the 2 sets, and given that the data set we have is fixed and small, if we make one set bigger, the other gets smaller. So that's the key challenge. So cross-validation is a way to, it's like a tug of war between the 2 sets in order to actually maximize our learning and testing. And cross-validation is a technique to actually maximize both with whatever data we have. So that's the key reason. So quickly, basically, when setting aside data for parameter estimation or training the machine and validation of results cannot be afforded, we actually use cross-validation to perform all these tasks. And popular use cases for cross-validation are to estimate generalizability, test accuracy, or test error. There's many other performance measures we can we would like to measure. And second is to pick optimal parameters, try out different parameters for the machine and see which ones are performing better, and to compare different models if you are actually trying to see if some techniques are performing better than others. So these are the popular use cases. Of course, it could be used in many other scenarios whenever out-of-sample predictions are involved. Typically in machine learning, these are the 3 popular use cases you'll be encountering. So there are 2 key aspects of cross-validation when you try to do it. The biggest one and the most important is how you split the data into training and tests. like Chris mentioned, is important. We actually maximize the independence between the train and testlets, and this split usually happens across samples. For example, when you're doing individual patient diagnosis, you set aside some healthy controls and disease and train on the remaining ones to make predictions on the rest. It could also happen, like healthy versus disease example. It also happen over time when you're trying to do task prediction within a subject. So you have a long time series from the fMRI data, and you would like to split the data into training test set to see if your classifier is able to make predictions well within a subject. For example, whether it can distinguish between cats and chairs in an fMRI experiment. And how often you repeat these randomized splits. The repetition is important because we want to make sure that we are not testing on some easy splits or hard splits. We really expose the classifier to the full variability in the data, so we can take confidence in the fact that it actually generalizes when we apply it into unseen future data. So ideally you would like to repeat it as many times as possible depending on your cross-validation design. So these are the two main aspects. There's many smaller details, but this is the two things you need to remember. There's another term we need to learn before we go into what are the effects of different cross-validation choices, that is called the validation set. So the need for this arises from the following facts. One, let's say we have this training set, we fit a model to it, we can assess its goodness of fit or how well it's able to actually learn the patterns within the data. And in a supervised machine learning case, we can actually compute many metrics to assess the goodness of fit. But given we used it to actually train the model is biased towards the train set. So we can use a separate test set that's independent from the training set to assess whether the learned parameters that are actually generalizing to new unseen data. And we actually randomize the split, repeat the process many times, so we can optimize the parameters for the model. But because we use the test set to optimize your model, it is biased towards the existing training and test set, and we would like to really measure how well it generalizes to completely unseen data in the future. So ideally, we would like a separate validation set that is completely separate from training and test sets, so we can actually estimate how well the fully trained classifier performs, generalizes. So this gives us a way to estimate its performance independent of the training and test set. So let's say this is our full data set, and this is typically called the inner loop in cross-validation, and this is typically referred to as the outer loop. These terms are helpful when you actually venture into implementing your own cross-validation or for your own particular complicated analysis. And it's important to remember that this could be actually extended deeper or broader depending on your needs. There could be multiple levels of nestedness. And yes, just to clarify before we go into the results, there are 3 splits, and of course the training set could be further split depending on the number of levels of parameters your model has. The important part is to actually not report the training error as the test error. That's what we need to keep in mind. So the purpose for the training set is mostly to train the model to learn its core parameters, so you can do everything you would like to with data and labels. The test set is to help optimize its hyperparameters, which are more like meta parameters, schemes and choices you make in training the model that cannot be easily estimated from the data. The validation set, you would like to use it to evaluate the performance of the fully optimized classifier based on the training and test set. This is the core purpose. What you don't want to do is to report, like I mentioned, training error as the test error. We need to keep that in mind, and we should never do any supervised analysis on the test set. For example, use it to pick your features in the model. That's one of the common mistakes. Or idea is if you want to test how well it's performing, you cannot use the label on the test set. It is that simple. And the purpose of the validation set is to report the results on a fully optimized classifier, so you don't want to use it in any way, either to train or optimize its parameters or hyperparameters. There are alternative names for this depending on whether you're on classical statistics community or machine learning community. So the test sets and validation sets sometimes could be interchanged. But the most important part is, as long as you implement it well and report the accurately, it shouldn't matter what name you use for the 3 sets. So now I'm going to give you a little more intuition into types of cross-validation. I think Chris already touched on this quickly, but I'll spend a little more time so you get a better idea. Let's say this is our full data set with some number of samples. And we can actually, the k-fold cross-validation splits the available samples into k number of approximately equally sized folds. For example, here I hope you can see the colors. And the idea is to take one fold as the test set in a given repetition of cross-validation or a trial, use the remaining to train your classifier, test it on the held out fold, and you repeat the process as you actually change the test set from 1 to k. So you repeat that k times. Every time you can measure accuracy or error, and you can either do median accuracy or error to evaluate its average performance or median performance. And the key point here is that the 4 folds are disjoint. That's the key point for k-fold cross-validation. And also remember that these folds don't have to be contiguous. We just show them to make it easier to explain. So the split could be all over the place as you randomize. And you would want to repeat this process multiple times, so you actually report results that are skewed to a particular split. Especially when you have a large number of samples, it's easy to actually find easy folds or hard folds depending on the organization of the data. So you want to repeat it as many times as possible. So another popular variant of cross-validation is something called repeated holdout, also called shuffle split, random subsampling, there are many names. The key point is you simply take the full data set and set aside a fixed percentage, 30%, 20%, depending on your data and goals. And you train it on the train set and evaluate its performance on the test set. Remember, if you need further optimization, you could further split the training set to optimize your parameters and hyperparameters, and you can recurse the process. But you always need an independent test set at the end to report your performance. And you could repeat this process a large number of times. And like I mentioned, the test sets don't have to be contiguous. They'll be all over the place. And in this particular scheme of cross-validation, there could be overlap among test sets, unlike the k-fold cross-validation, due to the nature of randomization. So hence you would like to repeat this process a large number of times, depending on n. So like 200, 300, and basically to the largest extent of your ability. That really helps estimate the performance in a more generic manner, also to give stable estimates. So these are 2 very popular variations, but there is many more variations depending on what k you choose. 10-fold is popular, but it could be 2 folds, which is split half, and it could be 3, 5, 10, like any number you choose. And like I mentioned, repeated holdout, depending on the amount of training percentage, it has variations. And also, when you split the data into training and test set, you could stratify it depending on your needs. Some classifiers are particularly very sensitive to this process if one class is really bigger than the other, like SVM is very sensitive to this process. You want to make sure that when you train it, you have an approximate size for all the classes in the data set. And this stratification could be across train and test set. So for example, if you have a very large control set, but also a small MCI, which is the mild cognitive impairment, And in order to avoid class imbalance, you would like to actually take equal sized chunks from both sets for your training set. So and then keep the remaining for test set. So you train only on the equal size splits and test on the remaining. This point is important depending on your classifier, especially if it is a support vector machine. The stratification can also be across classes depending on your needs. And another variant of cross-validation is you switch the size of the training and test set. Like I mentioned, large training set is better to train the model, but depending on the goal, the other may be more attractive to your needs. So there's another popular variant, like Chris mentioned, leave one unit out, where the unit could be any number of things depending on the goal, experiment, or analysis. It could be a sample for patient classification, or a pair, tuple, condition, task, block. There's many other variations. The key point is you always want to keep the test unit independent of the training unit, depending on your design. Otherwise, you're not really estimating generalizability. It's a lot of correlation. Defeats the purpose. So now that we know what cross-validation is, how to actually perform it, and what are the different variations, we would like to know what is the effect of choosing one of these choices. Like, is there an effect? How do we measure it? So the way we try to measure it is by, let's say we have this full data set. We have a particular, a smaller set from this whole data set and do some cross-validation to measure its performance, say accuracy. We can call that cross-validation accuracy. We take the remaining data and keep it aside and use the same model to estimate its performance on the held out validation set, and we can call it validation accuracy. If the cross-validation scheme we used had no bias or no structural bias, we would expect these to be approximately the same, because both are estimating generalizability. They should be approximately the same. However, in which case we call it unbiased. If it actually deviates from validation accuracy, either there is a positive or negative bias, depending on how you frame it. But this is the difference between cross-validation accuracy and validation accuracy that we use to assess the bias in a particular cross-validation scheme. So the results I'm going to present you are based on a large number of fMRI datasets that are listed here. I couldn't put all the information. You could refer to the paper at the bottom to get more. Briefly, there is a lot of the HAXP dataset, which is an intra-subject dataset with large number of samples and blocks, and many other open fMRI datasets that do inter-subject analysis. So based on this data, which is actually pretty large, we repeat the process I just showed you before, measure cross-validation accuracy and validation accuracy, and plot them from all datasets and all, using a few classifiers actually, just to get an idea, because what we are focused on is an accuracy, not the particular dataset. And what I am showing you here is the cross-validation accuracy on the y-axis and the validation accuracy on the x-axis. And you can immediately see that there is a large variation. It's due to the randomization and probably due to also low separability between the classes or the task. But there is large variance that needs to be remembered, especially if you switch across multiple data sets. And had there been no bias, it would have been right along the diagonal, and we call it we refer to it as unbiased. If the cross-validation accuracy is slightly lower than the validation accuracy, we refer to it as negatively biased. And if it is actually higher than the validation accuracy, it's positively biased. It's estimating the accuracy, optimistic sense, overestimating it, right? So one interesting trend we notice here is that in this particular area where it's negatively biased. Oh, by the way, all these results are coming from repeated holdout cross-validation scheme. We keep 20% of the data set aside for evaluation, repeated 10 times. So just, I forgot to mention that. And in this particular so in this particular region where the cross-validation scheme is underestimating the accuracy, it's in the high accuracy regions where it's from, let's say, 65% to 100%. So the negative bias is mostly on where the classifier is supposed to do well, and the positive bias is mostly in the low accuracy region. That is an interesting trend that needs to be kept in mind. I think this kind of pattern is usually observed from other studies too. So you really want to be careful when you are interpreting your cross-validation measurements, and keep this in mind, that it could be biased and there is actually a large variance. So this is done with one particular scheme of cross-validation, and we could actually repeat this process with other types of cross-validations to see whether where the bias and variance lies for different schemes. Right? For example, the popular variant of cross-validation is leave one sample out, and what I show here is this is the axis. If it's right in the middle by the unbiased tick, we don't see any bias. If it's to the right, we see positive bias from the cross-validation scheme. To the left, there is a negative bias, and we can immediately see that the bias from this particular scheme of cross-validation is very positive, almost 30%, due to the nature of correlations and also large variation, which is actually not desirable. And when you actually do the splits, ensuring that the full session or subject is left out, the bias mostly disappears. It's slightly negative actually, but there is still variance due to the correlations. And when you do the same thing with 20% left out, 3 splits or 10 or 50 splits to actually improve the stability of the estimates, the bias is actually reduced. However, the variance, I think we can still see it, be much smaller than the variance we saw on a leave one sample out case. So this is coming from real fMRI data where the ground truth is typically uncertain. We think it should be something, but we can't definitely say that because it's measured from the brain with multiple levels of uncertainties. So in order to see whether this is a problem, we actually generated some simulated data set with known ground truth. Because we generate it, we know exactly which sample belongs to which class and what their separability is, what we expect the performance to be, and if we make them easy to be separated, we expect higher accuracy. This really helps us to actually control the whole process and measure the bias in a more controlled sense. Just a toy example in 2 dimensions, but we actually repeat the process on a 100-dimensional data set. And whenever a temporal component is needed, we actually do add some autocorrelation to the data to reflect its real world situation. So on this toy data set, we repeat the same process, and we note that this leave one sample out process still has a large optimistic or positive bias with variance. And when you ensure that the split is actually in the independence between the training and test splits exists, the bias mostly disappears, and it could be it's the same case with repeated holdout cross-validation. And this is the key point: is if you don't ensure independence, you could have a large optimistic bias from the cross-validation scheme, right? So another point I would like to quickly mention is It's not enough to just properly split each fold into training and test sets and accurately evaluate its performance. That's the starting point. Because we repeat it a large number of times, we needed to, for example, here, right, each of these splits gives us to one estimate. It could be accuracy, error, or another popular measure called area under the ROC curve, which is actually a much better way to measure performance. But not all measures across different folds are commensurate. Commensurate as in could be directly compared on the same scale. We could be due to the way we measure it and due to the way the scale differs across different folds, right? Just to give an example, let's say this is our TIE data set and we train an SVM. It could be this, depending on how you optimize it, or in one particular split of data, or it could be this, right? So the reference point is changing when you produce predictions. The prediction scores Chris mentioned are actually like 0.3 in one fold may mean very different things in other folds. So you use it to build ROCs or compute AUCs. You can't simply put them together from different folds. This is a very subtle point that is easy to be missed when you just stop at the point, oh, I ensured that training and test sets are independent. That's only the starting point. But when you aggregate performance measures across folds, you really need to keep in mind that they must be commensurate when you pool, right? So one way to alleviate this or eliminate this problem, especially in building ROC curves, which are the receiver operating characteristic curves, is to use data only coming from the particular fold to build your ROC curves, compute commensurate measures, which is AUC per fold, and average the AUCs. So don't build an ROC coming from across all folds, which is a very bad idea. So CV is awesome. It helps us to measure generalizability under varying scenarios and under varying challenging situations. However, it does have its limitations, especially the number of times you need to repeat the process increases quite a bit with sample size, especially if you use repeated holdout, because you need to make sure we expose the classifier to its as much variability as we can. And moreover, if the particular model you're trying to fit, if the training time is high, this could be really a big limitation because it'll take a long time, depending on the number of samples and the model training time. Also, if the particular model has a large number of parameters, like deep learning, this is really going to bog you down. So just to keep that in mind when you perform cross-validation. So based on what we learned, I would like to recommend the following. So always make sure the test set is truly independent of the training set in all its aspects, in data, design, and labels. Very easy to commit mistakes in complicated analysis such as fMRI. And we recommend to you use repeated holdout, also called shuffle split in scikit-learn, for example. Choose a training percentage as large as possible depending on the data. Respect the sample structure or the dependency, so you ensure training and test sets are independent. And if you do have the ability to set aside some data, you use the biggest test set and repeat the process a large number of times. Really simple. So take-home messages or results could vary considerably with the different cross-validation scheme, because if you switch between different softwares, based on your needs, you have to keep in mind that you may be using a different cross-validation scheme. It may be optimizing in a different manner, and results could vary considerably. Let's say if you repeat the process only 10 times, come back a week later, try it again, you may have different results depending on your data. So don't forget that. So you need to repeat it a large number of times so you can take confidence in the fact that 3 months later when you publish the paper, results are similar, not different. And they can have variance depending on the scheme. It could be large. So you always want to make sure you report the full details, what kind of split, how many times you repeat it, the full distribution, not just the mean or the confidence interval, but the full distribution. And proper splitting is not enough, that's just a starting point. Proper pooling is needed also. So for example, when you report the results, don't just report the mean or the standard deviation, but try to report the full distribution. Just a simple example here. So these are the references where you can learn more details about the data I presented, and also general in-depth or broader types of discussion into cross-validation. Some tools you could use to make your life easier. And I would like to acknowledge my employers and other universities where I did some of this work, and especially the data. Enormous amount of computation has been done at Parietal in Bertrand's lab with Gail. Thanks to them. I did the simulation parts. So time for some cross-validation. Any questions? Do you want to use the mic?
Hello, it works? Okay.
Yeah.
Thank you for a very, very nice talk. So what you show is that there seems to be no bias if you have completely independence between your test and training set. What about a possible bias in your variance estimate on your accuracy? So it seems like you decrease the variance estimate as you go up in your splitting, so more splits equals to lower variance?
Yes.
How do you fix that? Or any recommendations on that?
To my knowledge, I think there is no unbiased estimator of the variance of these estimates from cross-validation. The best you can do is to, like you said, make sure the splits are independent and repeat it as large number of times. There isn't a clear recommendation there. It's open-ended research.
Okay. All right.
Except in very controlled situations with parametric models, and where data has clear data actually satisfy the properties of the techniques we use to estimate it.
Thanks.
So these the second reference actually does very theoretical assessment of these problems. So there may be a little more information, but to my knowledge, there isn't a clear recommendation in that direction. Any other questions?
Thank you. Sorry. Thank you for the talk. My question is, when we split the data, is there a consensus currently? How many folds should we use? What the
No.
number of folds the best?
No.
So we can just split the data arbitrarily.
Up to you.
Our needs.
Yes.
It's some sufficient number.
Yeah, so I mean, based on there's few people who've done extensive comparison. Tenfold is often recommended for some reasons, but it really depends on your data, what kind of applications you have. But tenfold is a good number. It's quite popular, you know. Sorry, it cannot be any more theoretical than that.
So, hi, thanks. Great talk. So, I mean, can you just follow up on that a little more? Because I've definitely heard tenfold is preferred over, k-fold, or, leave one out. So what exactly is the reason for that then? Is it the higher variance estimate with the leave one out than
Yes.
the tenfold, but they both have zero bias if you make sure your data are independent? Is that
Yes.
the summary?
Yes.
Okay, thanks.
Yes. Yeah, the problem with leave one out is not just its scheme, how people commonly apply it, depending on the level of complication in their analysis. So as you showed, if you do leave one session out in your fMRI analysis, for example, the bias mostly disappears. Right? But repeated holdout has, it gives you more opportunity to estimate few other things from the scheme, whereas leave one session out cannot. Right? You can control the size of the test set in repeated holdout, whereas leave one session out, you only have one session. Right? So that's its limitation. A correlation is high across the training sets. Sorry, the overlap across training sets is high. That leads to that leads to overfit in a sense. And when the data changes, it's not able to make correct predictions.
Thank you for that talk. You mentioned that there could be potential leakage unless you have like 3 separate sets, validation set and outer loop, and then you can do like a nested cross-validation loop inside. Is there like a suggestion on the sample size then? Because most of the people, they're restricted by sample size in a study. Let's say, you know, for example, one study may have 60 or 80 subjects. Would you then, you know, what's the sample size? Basically, that's my question. How can you really try to get to this problem if you have just limited samples in your study?
Well, I mean, the purpose of cross-validation is to assess all small sample sizes, use all the data you have. That's what I would say.
I see. So again, the number of splits, it's sort of variable depending on the size of your data set, and you can manipulate.
Right. I mean, so what I presented are only a subset of what is possible. You can indeed do exhaustive cross-validation. Try make sure all the subjects are part of the test set at least once or twice, or they were all at least part of the training set once or twice. That exhaustive search could be really, really slow. If you have 500 subjects and you want to make sure only like 20 subjects are chosen for the test set each time, it's a 500 C2, which is a very large number. Like even if you have a very large HPC cluster, it could take weeks to go through the combinations. You really don't need to do that most of the times, as long as you do it a few hundred times.
Thank you.
No problem.
Hi, thanks for the talk. I just have a quick follow-up question regarding like the choice of the cross-validation method. I'm just wondering if like in a situation like, let's say like very unbalanced sample, let's say like one group is 100 subjects, the other is like 10. In this case, do you still recommend like using k-fold, or you still like, or you recommend using like the one out?
Like I showed in one of the slides, depending on the classifier you use, for example, SVM is very sensitive to class imbalance. You want to stratify your training set. Let's say if you were to use SVM. If you have 110, it's actually extreme level of class imbalance. One thing to remember is you always need at least 1 or 2 samples in the test set from all the classes.
Yeah.
In order to actually test whether the classifier is learning. Because remember, this is not regression, it's more a discrimination problem. We're training it to discriminate, not recognize. Right? So you need to make sure that you have all the samples represented in the test set. Other than that, like let's say if you were to use tenfold in your case, you will have only 1 from the minority class, which is not a great way to test your classifier, but that's what you can do. But you need to make that clear. And maybe there are some approaches to ameliorate or reduce the effect of class imbalance, something called SMOTE. It's a kind of a bootstrapping technique with replacement to boost up the sizes. But in such cases of like 10 versus 100, like those are just tricks. You would have really like problem getting a good estimate. We could talk about this further. I think we are running out of time.
And for that, I think maybe Janina, the one class SVM, because there's more looking at outliers from the normal population. So the question now is different in your case, because you have so few subjects compared to the other class. So there is more, I have the representation of the normal class, and those are outliers. So you would use maybe different techniques than standard classification, where you're assuming that you have enough samples from all your classes.
Yeah, thank you.